Okay, so in this part, we're going to look at some of the example problems associated with Hooke's law. So now that we have the equation, what do we do with it? So here's a typical problem that you might see with Hooke's law. Again, you see graphs a lot of times when there's Hooke's law problems, and they always have force on the y-axis, which is why we did our lab with force on the y-axis, even though it was the independent variable. So in this problem, we're given that the graph is described by the equation F equals 50 newtons per meter times x. So we're already given a little data about this particular spring. So the first question is how much force is required to stretch the spring 0.25 meters? Okay, this is a really straightforward one. Since we're given the distance and we are already given the equation, we can simply put it into the 0.25 meters into the equation. The only thing you have to watch for is to make sure that if the spring constant is in newtons per meter, that the distance is also in meters. The same thing would be true if they gave you the spring constant in newtons per centimeter. You would then want to use centimeters for your displacement. As long as the distance unit is the same, it doesn't actually matter what it is. So here we find the force to be 12.5 newtons, which seems fairly reasonable for this type of spring. So next up, we're going to talk about how far does it need to be stretched to store 20 joules of energy. So we want to be careful this time that we don't use the equation that was given, because the equation that was given is talking about force and displacements. Now we're talking about energy. In this case, we had already derived the equation for elastic potential energy. So that's the 1/2 kx squared deal. So they gave us the 20 joules of energy, so we put that in for EL. The subscript EL is for elastic, the capital E is for energy. So we have 20 joules here. We put in the 50 newtons per meter spring constant, we solve for x. Occasionally I have students who forget to take the square root of their answer, so be sure to make sure that you do that. So that would be our part B. Pretty straightforward. Part C, now we're going to look using the graph, we're going to try to answer some of the same questions. So in this one, we're going to find the energy stored from 10 to 20 centimeters. So the first thing we want to do, this graph wasn't given, we weren't given any numbers on this particular graph, so we want to figure out how to scale it. It should be pretty practical if we're trying to make sure we get to at least 20 centimeters to scale it by 5 centimeters for each increment. Since we have 1, 2, 3, 4, we have 5 increments, so 5 centimeters would scale it pretty far all the way across. We want to use as much of the graph as possible. So when we do that, we can find out, I went ahead and put the numbers on the bottom then all the way across, and now we need to figure out how to scale the y-axis. Since we are already given the equation here, we can scale the y-axis by putting in each of these x values into the equation, and you'll notice a pattern. You don't have to use the equation 5 times, but when we put it in for when we put 0.05 in for x, we find the force then to be 2.5. So we can go through then and scale the graph that way. So now that the graph's all scaled, we'll go back and try to answer the problem. So we're actually looking to find the energy stored stretching it from 10 to 20 centimeters. We previously defined energy as the area underneath the curve when you have force versus stretch, and we know that because the unit becomes a newton times a meter, and a newton meter is a joule, and that's something that you should memorize. You should know a newton meter is a joule without having to think about it. So in this case, it seemed easy to me to break up that area into a triangle and a square. You could do it a different way, but that seemed pretty simple to me. So here we have the formula for the triangle and the square, and we just go through and put the numbers in for each. So we have the difference in base as being 0.1 for each of them, and then the difference in height is actually 5 for both of them, just the way that this graph happened to work out. We just have the 1/2 in front of the triangle equation. So we do the math on that, add them all up, and we find that the elastic energy stored, when we find it graphically, is 0.75 joules. So we're going to go back and, since we did this graphically, we'll go back and do it with an equation and see if the two of them match. And actually, while I'm at it, I'm going to show you a different way that you could have done it graphically as well. So same kind of thing, same question, but we're going to try to do it mathematically. And do pay attention when you problem solve to see if they tell you which way you need to solve it. If they don't tell you, then you can do it any way you want. Okay, so here we're going to do it mathematically. So this is what I meant when I said I'll show you another way to do it graphically. The first time we did a triangle and a square, here I did a big triangle, and we're going to subtract out the little triangle. So what would be left would be what's shaded in purple here, which is the same area as we found before. So that's actually a different way to do it graphically, but I did put it on here as a visual for the way that we're going to do it with the equation. So the total energy that we're going to find is we're going to find the energy stored in 20 centimeters and subtract out the energy stored in 10 centimeters. And that difference will be the energy stored from 10 to 20. Now, another reason I wanted to show you this image was because I think it's most students' first impulse to look at the equation 1/2 kx squared and just put in 10 centimeters for the x, because the change in x is 10 centimeters. But I think you can see by looking at the image that this yellow triangle represents the energy stored in 10 centimeters. So if all you do is take the difference in the distances and then use the equation once, you will find a much different answer than if you use the equation for 10 and the equation for 20. And if you find the difference between those two equations, you will find a much different answer. So that's why I wanted to show you the picture. The math then, once you understand that concept, is not difficult. We're going to take the equation for the energy stored at 20 centimeters and subtract out the energy stored at 10 centimeters. And here again, if I want my distance unit to match my spring constant. So since my spring constant was newtons per meter, I did go ahead and convert the distances into meters. So I take the difference between the two, and I find 0.75 joules, which is the same answer that we had before. So to review then, if they don't tell you whether you should solve it mathematically or graphically, you can do it whichever way you want. If they do tell you, then make sure that you do what they ask. Do pay attention that you can't just take the difference in two distances. If the initial stretch is not 0, that's when you have to do this subtraction thing. Okay, so here's actually, that was the last part of that problem. That's good. On your worksheet that you're going to be doing that's associated with this section, you'll do some basic Hooke's Law problems, and they're really, I don't think they're too difficult. The things that kids mess up are mixing up when to use the force equation and when to use the energy equation. If they ask you for energy, you cannot use F equals kx because there's no energy in that equation, so you can't interchange the two. Only use the force one for force, the energy for energy. You will also see on the back of that worksheet, they ask you a couple questions that's kind of like this picture. But I thought that was funny. Not really funny, but entertaining. Where you have a box. My picture is a box, but this guy's kind of more interesting. So he's just sitting there, and then you have to answer some questions about the force and energy in the spring in that situation. You should be able to apply what we talked about in the examples to that, so I'm not going to go through one here. However, if you have trouble, we will most definitely go over it in class. So that is the end of the Hooke's Law discussion, and we will continue on by studying energy from here. So we don't spend any more time on Hooke's Law, so if you have trouble, make sure that you come in and get it figured out with me. All right, thanks.